How's it going, ladies and gentlemen? Mr. Donahue here. Gonna go over how to determine bond type. If you add two elements together and they react, what kind of bond will you get? Will it be ionic, covalent, or what kind of covalent bond will you get? All right. So first, what is the difference between these things? What's the difference between the kind of bonds? I got a nice video that I found on YouTube. Let's go to it and watch.
Welcome to Dogs Teaching History. Our first lesson is chemical bonding. Chemical bonds are what hold atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in a chemical bond are covalent. Involve the sharing of a pair of valence electrons by two atoms. There is also what is called polar covalent bonds. These are covalent bonds. Thanks for watching, and we'll see you guys next time.
So cute. All right. So those are the different kinds of bonds. So what determines what kind of bond will form? Which one are we going to get? And the answer to that is electronegativity, right? It's all about the difference in electronegativity, which again is an attraction for electrons in a bond. Now, how much does an atom want an electron? It's like a tug of war between the two of them over the electrons. So if we got a nonpolar covalent bond, it's definitely going to be between two nonmetals. So if you got two nonmetals bonding together, it's definitely a covalent bond. What makes it nonpolar is that there's an electronegativity difference of 0. So they would have to have the same electronegativity. So an example would be like hydrogen bonding with hydrogen. All right, they definitely have the same electronegativity because it's the same element. So let's go to an awesome, cool simulator on PhET that'll help us show it. So here we got two different atoms, A and B, right? And they have adjustable electronegativities up top, so you can play with them. And right now, let's just both set them to the max so that they have the same electronegativity, right? So what this gray cloud is showing the electron density, right? The less dense it is, the less electrons are there, the whiter it would be, and the more, the darker it would be. You can see right here, it's gray all throughout. So it is, they're shared equally. You'll find electrons equally in any part of it. Doesn't matter where you look. A real example would be hydrogen, H2, right? So both hydrogens, they have the same electronegativity, right? 2.1, or whatever your chart tells you it is, 2.1 here. So if you were to look at the electron density, it's going to be the same anywhere you look at it, right? It doesn't matter what part of the molecule you look at, it's the same. All right. Polar covalent bonds, again, is going to be between two nonmetals. But in this example, one atom is going to have a higher electronegativity than the other. So we're going to get unevenly shared electrons. One atom wants the electrons more than the other and is essentially hogging them. It's, taking them, having them for a longer time. So an example would be like HF, right? So I got hydrogen and fluorine. All right, fluorine is the more electronegative one. So if I was an electron, I would spend more time around the fluorine than I would around the hydrogen. Right, and be like, all right, cool. Now I'm going to go hang out with the fluorine again because he wants me more. All right, once around the hydrogen and a bunch of times around the fluorine. All right, so it's not evenly shared. So let's check out an example using the simulator again. All right, so that would be kind of like this, right? You can see as I start to make one atom less electronegative, and fluorine would be like B, it would have the most electronegative. You start to see, all right, well, this side's darker than that side. So this side has electrons more often. And what do we know about electrons? Say they're negatively charged. All right, very good. They are negatively charged, so if it's spending more time around this atom, then this atom is going to become slightly negative. And you can see as the difference gets bigger, that charge gets bigger too. Right, so if we had really different electronegativities, you get a really slightly positive charge at one end and a really slightly negative charge at the other. All right, so a real example would be hydrogen fluoride. So you can take a look down here on this end. It's a lot whiter than at the other end. So the electrons don't spend as much time around the hydrogen as they do the fluorine, which makes the fluorine a slightly negative charge, whereas the hydrogen would be slightly positive. So that's why we call it a polar bond. You can kind of see there's like a north and a south pole, right? You can kind of see, all right, well, one end is definitely more negative than the other. So that's why we call it a polar bond. All right, and then ionic bonds. You know, it's going to be between a metal and a nonmetal. So this is different, right? Whenever you have a metal and a nonmetal bonding together. So for example, let's say calcium oxide. The oxygen has such a greater electronegativity than the calcium that it just takes the electrons from the calcium. Right? There's no sharing at all. It's a complete transfer. So an example down here would be sodium chloride, right? That electron that sodium has is going to be lost and given to the chlorine. So what you end up with is Na plus because it lost an electron, and Cl minus that now has 8 valence electrons. All right. And what do we know about opposite charges? Say they attract to each other. They attract to each other. Perfect. So now we have a positive ion and a negative ion, and they're going to be bonded together ionically. So that, in a nutshell, is how you determine what kind of bond you're going to get between two elements. All right.